Okay.
Oops.
Okay. Good morning, everyone. Welcome to a new session of the research seminars for the IEC. Today we welcome Juan Cortina to give us the talk. Juan completed his PhD at the Universidad Complutense de Madrid, working in cosmic ray physics. Was a researcher at Max Planck for Physics in Munich and Institut de Física de Altas Energías in Barcelona. He's currently staff researcher at the CMAT in Madrid, and during the past 30 years he has worked in experiments such as the HEGRA cosmic ray detector and the Very High Energy Gamma Ray Telescope HEGRA, MAGIC, and CTAO. He served as a spokesperson of the MAGIC collaboration and is currently in the management of the CTAO LST collaboration. And today he's going to talk us about the gamma ray astrophysics, the multimessenger, and Canarian connection.
Okay, thank you. Thank you for the introduction. Thanks for the invitation to give a seminar here. Today I'll be talking about gamma rays. I cannot help to talk about gamma rays, but I'll try to stress more the connections with the other messengers. So the multi-messenger, say, side of gamma ray astrophysics, and I will be talking about some interesting connections with the Canary Islands and gamma ray astrophysics and the Canary Islands. So what are messengers? What are these messengers we are talking about? I guess everybody knows by now, but I will introduce them. How we detect them. A very quick introduction to mono-messenger science, very quick. And then I go deep into multi-messenger, okay? Both galactic and extragalactic. And then I will finish with some maybe prospects, what we can expect in the future. So messengers, what are these messengers? I'm sure you heard about gammas and photons in general. So photons is how essentially we did astronomy so far. And here I'm talking from bare eyes to Galileo to all the telescopes, from radio to gamma rays, okay? Multi-wavelengths. It's all photons. So that would be the something. That would be the first messenger, say, the photons. But then we got other messengers, and here what you see are more other elementary particles that we know. And we know about quarks. We know about up and down quark, and we know about electrons, right? So these we can also use as messengers. We can also get these particles directly at the Earth and we can detect them. And that will be the second messenger. When they have a lot of energy, they reach us as cosmic rays. So that would be messenger number 2, cosmic rays. They are more elementary particles. You got neutrinos. So neutrinos, electron, muon, tau neutrinos, they could be messenger 3. We are also getting neutrinos from the cosmos. We can learn about the cosmos with neutrinos. You show all the particles in the standard model. Unfortunately, many of them are not, their lifetime is too short, so they don't reach us from the sources. So we had to eliminate those. But as you can see, all these are elementary particles in the standard model. If you want to go to the next messenger, you have to go beyond the standard model, actually. You have to consider general relativity, which is not yet in the standard model of particle physics. Gravitational waves. So gravitational waves are a consequence of general relativity. So this would be my messenger number 2, number 4, right? 4 messengers. And if you want to speculate and go even farther beyond the standard model, you may, for instance, consider that you may have a full ensemble of supersymmetric particles, counterpart partners to the standard model particles. And this could be the dark matter. So, right, we could also study the universe through these 5th messenger dark matter particles, whatever they are, because it gets less and less clear, I would say, with time. They may be supersymmetric particles, but they may also be actions, maybe primordial black holes, which are not really particles. There may be things like quark nuggets, whatever they are. Okay, you may put all of them in the same pot and call them messenger 5. That matter. Okay, so together is not just you get particles with an energy, so you get actual real spectra from all these messengers. So you are very much familiar with the photon spectrum, the multi-wavelength spectrum, going all the way to beta electron volts, 10 to the 18 electron volts, from radio to very, very, very high energy gamma rays. But you also have a spectrum of neutrinos, starting mainly around here, but going all the way up. And cosmic rays are starting around MeV energies as well. Then you got a real frequency spectrum of gravitational waves as well, from microhertz to kilohertz, and even beyond. And dark matter, well, you may argue that you may have a spectrum as well, whatever they are, okay? So how we detect these messengers? I will start with gamma rays, okay? Well, I used to think that Bajada de la Virgen made La Palma unique. It's a unique thing on La Palma. But then this year I realized there's also a Bajada de la Virgen in Hierro. So it's not so unique anymore, La Palma. And then even there's a Bajada de la Virgen in Getafe. So, I mean, there's nothing unique of La Palma in terms of Bajada de la Virgen, but there's something really unique in La Palma. That is that we've been looking for gamma rays and detecting gamma rays from the ground since the 1990s in La Palma. I mean, it's been for more than 30 years now. The HIGRA telescopes were the first imaging atmospheric Cherenkov telescopes. They were kind of small, only 4-meter diameter. Okay, you compare it with optical telescopes, they're huge, but for Cherenkov telescopes, they're small. There were 6 of them in HIGRA, and they operated at the end of the 90s. They made the first galactic scan. They identified the first, or they didn't identify, they found the first unidentified source, which remains unidentified, really. And they detected the first supernova remnant emitting at these very high energies. Then we had MAGIC building on HIGRA, By the way, Hydra was the first array of many telescopes in the world. Okay, pioneering. Magic was, or is, 2 telescopes still running. It went to even lower energies, less than 100 giga-electron volt gamma rays. And it's still operating. And there's a number of first discoveries made by this, like the first quasar, the first pulsar, the first GRB detected at very high energies. And more interesting for this talk, the first association of a gamma ray and neutrino source. We're building now the CTAO telescopes, and here what you see is Magic plus the first LST large-size telescope, which is already there since 2018. Okay, going to even lower energies and targeting even higher sensitivities. Now we even have 4 LSTs. If you go to La Palma, you will see now 6 telescopes, the 2 Magics and 4 LSTs, which should finish installation next year. Okay, and then this will become the most sensitive Cherenkov telescope array in the world. Okay, starting next year when it finishes installation. The major partners, Spain, Japan, Germany, and France, and Spain is having actually the majority participation in this project. This will not stop there. We will have even more CTAO telescopes. We will add 12-meter telescopes, medium-sized telescopes, also in the near future, and this will run for 30 years. Okay, so this will be a reference instrument for 30 years. It's not only La Palma, actually now you also have Cherenkov telescopes at Teide, and this was a spin-off really of CTAO, but there will be the ASTRI mini array at Teide with telescopes similar to Hydra. There will be 9 of them, targeting the highest energies. Okay, but there was a road that we didn't take. Let me explain why. There was a road that we didn't take because there are 2 ways to detect gamma rays from the ground. One is with Cherenkov telescopes. You get a gamma ray, you produce always a cascade of particles. These particles can produce Cherenkov light and be detected with these Cherenkov telescopes, right? This is how imaging atmospheric Cherenkov telescopes work. But you may also detect the particles in this particle shower. You may have detectors, normally at higher altitudes, that detect the shower, and from the timing of the particles, you can also reconstruct the direction of the gamma rays. So that's something we used to do back in the 90s, even before the Cherenkov telescopes. We had this array of particle detectors with slightly higher energies. There were scintillator, muon detectors, and they were used for cosmic ray and for gamma ray detection, actually, at the same time, cosmic ray and gamma rays. And we managed to measure the spectrum and the composition of the cosmic rays, but we didn't detect a single gamma ray source. Okay, so we gave up on this. We gave up on this technique. But others didn't give up. I mean, the Americans mainly continue to build this kind of particle detectors, in this case, inside big water pools to detect the particles. They went in size from a few square meters to 40,000 square meters in a detector in Mexico called Hawk. Lately, the Chinese have also got into the game. And this is a map of rocket, and this is where Hydra used to be. This was the size of Hydra, 0.04 kilometers squared. Okay, what the Chinese have built is, oh, it's hard to see here. Sorry. It's an array this size. Okay, so it was also shown here. It's as big as essentially the whole observatory. Okay, and it's full of these detectors. If Hydra was here, there are 5,000 detectors, particle detectors. There are 1,200 muon counters. We have 20 in here. Okay, with this huge detector. And they also have water Cherenkov detectors in here. Okay, so with this huge array, they have a lot of collection area. They have also a lot of power to discriminate gammas and cosmics. So they finally managed to detect sources of gamma rays at high energies, but with large size because their angular resolution is not so good. But they finally managed to detect sources up to 1 beta electron volt or so. I will come back to this. So now we have a full ensemble. So now we have the running experiments and around GeV and TeV energies, imaging atmospheric Cherenkov telescopes. We are building CTAO, and we have LASO also at even higher energies, okay, up to 1 PeV, beta electron volt. And at lower energies, we still have Fermi-LAT for a while, maybe not in a few months. There's actually no successor mission for Fermi-LAT at lower energies. Okay, so we have a lot of detectors of gamma rays. So what happens with cosmic ray detectors? So we have a space cosmic ray detectors. Many of them, 3 of them are sitting on the International Space Station. The best probably is well, the best for sure is AMS, where IEC is actually also involved. With areas of 1 square meter or so, there's another Chinese experiment at the same area. But we can also detect gamma rays from the ground, right? So we can detect them. They also produce showers, and you can also use the same particle detectors to study cosmic rays from the ground at higher energies. That's what's been going on. It was done with Hydra, but it can also be done with LASO and with all the experiments like Cascade and so on, but mainly with Piero J, which is an experiment in Argentina, which is huge. I mean, here you can see several towns in Argentina, and it's as big as 3,000 square kilometers. Okay, so this is how you detect cosmic rays at the highest energies. Neutrinos. Neutrinos are, you place your hand like this, you get 1 trillion neutrinos every second. And if you are lucky in your whole life, 1 will interact with your hand. Okay, so they are difficult to catch, these neutrinos. You can use 2 reactions. Allow me to show a few nuclear reactions. Neutrinos could interact with nucleons, and they could generate the corresponding lepton. So electronic neutrino would generate an electron and would change from proton to neutron and vice versa. And neutrinos can also kick actually the nucleon, accelerate the neutron. And this is the way you essentially detect that. The same for muon and tau neutrinos, but unfortunately the cross sections for these reactions are very small, so that's why it's so difficult to detect them. So you need many protons and neutrons, so you need a huge volume, you need a lot of mass as a target you want to see a neutrino. And you also need to get rid of the horrible atmospheric background of other atmospheric neutrinos and muons and stuff that is coming from cosmic rays in the atmosphere. So that's why you need these huge detectors. Like I'm sure you heard about Kamiokande. You get this Japanese down here sitting on water. It's a huge tank of water where you got a neutrino can produce a muon. The muon produces Cherenkov light in the water, same as our atmospheric showers in the atmosphere. And then you detect the Cherenkov light. You reconstruct the direction of the neutrino like this, okay? If you use heavier materials, you can reduce the target volume, but at the end, the technique is very much the same. It's based on these reactions I showed you before. Now, the name of the game is actually detectors like Kamiokande, still a bigger version of Kamiokande, Hyper K, and Dune, which is under construction in the US, okay, with 40 kiloton of liquid argon, okay, which is very heavy. It's a very heavy element. And it's underground. All these guys are underground to avoid this background. But if you want to go to even, this is for essentially for MeV energy. So if you want to go to even higher energies like tera-electron volt, you need even higher, bigger volumes, and you need to essentially equip 1 kilometer cube of volume to detect something. And that's how, for instance, IceCube works. Is inside the ice of Antarctica, of the South Pole. And the way it works is this background is coming from cosmic rays that produce muons and neutrinos. So you look down, you want to find neutrinos coming from an AGN down here. Okay, it's impossible because you get a lot of muons and neutrinos coming from the atmosphere. You have to look down. You have to look through the Earth to get rid of the muons that are produced at the other side of the Earth. Okay, so that's why IceCube mainly looks down through the Earth. The same is happening. This is IceCube, so this is there are a lot of PMTs in the ice, have a depth of 1.5 kilometers down to 2.5 kilometers. Okay, covering one's cubic kilometer. Okay, this has been running for a while, more than 10 years already. Okay. Instead, KN3net is another one that is in water. There are actually two arrays, two detectors. One is near Sicily, it's called ARCA, and is as big as 1 kilometer square. Okay, this is the Eiffel Tower as a reference. And then you get another one that is only as big as the Eiffel Tower. Okay, that is at the French coast. It's called ORCA, but it's all part of ARCA and ORCA are part of KN3net. Okay. These are under deployment. So today they are, all, for instance, only 28 lines out of 100 lines, so still partially equipped. This is going on, but it will be in size similar to IceCube, but it will be in the northern hemisphere, right? So it will be looking down. It will be looking at the southern sky. So this is what you got in neutrino detectors. So you got IceCube running for a long while, and Tares was before. And then KN3net, ARCA, and ORCA under deployment. ARCA is for higher energies, starting at 100 giga-electron volts. ORCA is more dense, and it will reach down to 1 giga-electron volt. Okay, so this is the ensemble of neutrino detectors right now at the highest energies. Okay, so what kind of sources we detect with these kind of fancy detectors? So photons, you know very well. I mean, and I will only talk a bit about the highest energies. Here is mainly non-thermal sources, okay? And it's compact objects, the surroundings of compact objects, interacting compact objects, black holes, neutron stars, the accretion jets that surround them, like X-ray binaries, AGNs, and GFBs, right? You get wind shocks in binaries. Okay, so wing collision also accelerating particles. You always accelerate cosmic rays like this, and then you produce the gamma ray. You get supernova and supernova remnants, right? For neutrinos, you may get really neutrinos from the Big Bang, very hard to detect. You get essentially two ranges: MEV neutrinos coming from the sun and from supernovae, and non-thermal sources, and those are essentially the same as the sources of cosmic ray and neutrinos and gamma rays. And then you may have some cosmogenic neutrinos coming from the very, very, very highest cosmic rays interacting in extragalactic space. For cosmic rays, again, you got solar cosmic rays, and again, you have very high energy, much higher energies cosmic rays. Gravitational waves, I'm sure you heard about the LIGO and Virgo detectors, the detections. These are mergers of compact objects, black hole mergers, really, at kilohertz frequencies. And now the idea is to explore down to millihertz or even microhertz with LISA in the future from space. You may also have primordial gravitational waves, and that's where actually all these pulsar timing arrays are also targeted. And dark matter, I mean, the problem with dark matter is not the sources, is we don't even know the messenger, right? As I told you, it may be WIMPs at energies of giga-electron volt to tera-electron volt. It may be actions or action-like particles at much lower energies. So now that it's not so clear that WIMPs will be the dark matter particles, the search has extended to a lot of candidates. Dark photons, it could be even macroscopic dark matter. Okay, because here I mean, we know much less, right? So what is the connection between all this? What are the sources that are common and how we connect them? And there are actually two sweet energy ranges. There are two energy ranges where there's clearly a lot of multi-messenger exchange of information. One is the MEV. I mean, MEV range, in the MEV range, the sun is producing solar flares, it's producing coronal mass ejections, and they accelerate, they produce cosmic rays up to tens of GeV, which are visible in photons. So actually the first, if I'm not wrong, the first multi-messenger event in history was in February 28th, 1942, when Forbach detected an increase in cosmic ray flux along with a solar flare in H alpha. Okay, I think was the first multi-messenger event. But then you got also neutrinos coming from the sun, MEV neutrinos, first detected by Davis in Homestake, which eventually gave rise to 2 Nobel Prizes, actually. Okay, I don't think it's even enough with 2 Nobel Prizes. This has been so fundamental for physics that. And supernovas are also expected in MEV. You expect a lot of neutrinos from supernova, and of course you expect photons. And only with supernova 1987, which were 30 neutrinos were detected. Only with that, I mean, the impact was so huge that you could see that 99% of the energy of the supernova goes into neutrinos. And that came from those 30 neutrinos, right? So the cooling of the neutron star is very fast. You could also establish the delay between the neutrinos and the photons, right? And this allowed to measure the speed of the neutrinos. And it's essentially the speed of light, as expected, but you need to measure it, right? And you could also measure the lifetime of the neutrinos. This was the first sweet energy range, MEV, but the second sweet energy range is non-thermal sources. And here you got compact objects. Again, I described them before. And the trick here is that when protons, cosmic rays, you always accelerate cosmic rays because they are charged. And then they generate pions, and pions generate gammas, and pions generate muons and neutrinos. Okay, so at the end, you get neutrinos and gammas that have a fraction, like 10% or so of the energy of the initial proton. Okay, so that's the key to the full multi-messenger connection. You accelerate cosmic rays and you get neutrinos and gammas. Okay. Of course, neutrinos, they can travel unhindered all the way to the Earth. Cosmic rays are deflected by magnetic field, so you lose all information about the direction. And gamma rays, they also travel straight, but sometimes they suffer absorption. Okay. So you want to study this source, and you got to deal with all these effects. If you are able, neutrinos are very hard to detect. That's the problem with neutrinos. But if you are able to see neutrinos, you for sure know that there was a proton acceleration here. Okay. So what do we know about cosmic rays these days? So you've seen this plot already 1,000 times, probably. Okay, this is the latest one, say, including all the proton, helium, oxygen, iron spectra, and so on. And in this huge scale of many decades of energy, you don't see the details, but lately, well, let me say that we believe that this part here is coming from galactic, sources, and this is coming from extragalactic sources. Okay, so these are the highest energies, and this is up to 1 beta electron volt, so 10 to the 15. So, sorry. Okay. So what are these galactic sources? So there's something called the standard model of cosmic rays. The standard model of cosmic rays tells you that galactic cosmic rays, so all these guys here, all the blue part of the plot, are accelerated in supernova remnants, shell-type supernova remnants. Okay, that's the standard model. Now, and this is also very new. This is from this year. You look at the proton and helium spectra. You look at the cosmic ray spectra. We are starting to see, and this is from the last 10 years, we're starting to see a structure inside the spectrum. So it's not just a power law, a flat power law, flat and boring power law. You start to see a lot of structure in the proton, in the helium spectra, in the electron spectra, in the positors, and so on. So you see up to 3 bumps. This is coming from LASSO, and it's very, very new. It looks like there's a third bump close to 1 beta electron volt. Okay, so there must be something there. You may speculate that there are several source populations, like maybe you don't only have supernova remnants, maybe you have something else. You may even have just one individual source, just one supernova remnant in the whole galaxy that is producing this bump in the cosmic wave spectrum. Okay, we don't know very much from this spectrum, from the spectrum itself. Now, in the standard model of galactic cosmic rays, everything is coming from supernova remnants. And here you accelerate protons, and then you produce gammas and neutrinos. Okay. Unfortunately, you also accelerate electrons, and they produce also gammas through inverse quantum. And this is a terrible background. So it's hard to tell if you accelerate protons or you accelerate electrons, because you always get gammas from both of them. Okay. Neutrinos could be the real smoking gun. If we could detect the neutrino from a supernova remnant, we would know. Now, how is this a standard model of cosmic rays doing these days? So it's doing well at the lowest energies. So around 1 giga electron volt is doing fantastic, because we learned something new with Fermi. We learned that in many supernova remnants, this was one of the first, you would expect the electronic components, so the electrons, to have a flat shape. While for hadron, you expect quite some drop in the spectrum at the lowest energies. And you see the drop. This is the so-called pi-zero bump. Okay, so this pi-zero bump, this drop in the spectrum, you see for many supernova remnants now. So you know that they are hadrons accelerated to supernova remnants. Okay, so they really produce hadrons, but that you only know at the lowest energies. Okay, for sure you know that they are hadrons at 1 giga electron volt and so on. So they produce cosmic rays. Unfortunately, when you look at the highest energy, the problem is when you look at the gamma ray spectra of supernova remnants, you systematically see a drop in the spectrum at the highest energies, close to the knee, close to above 1 TeV or 10 TeV. This is the case for Cassiopeia A. And so you know Cassiopeia is a young supernova remnant, where you would expect a lot of cosmic ray acceleration, but there's no cosmic ray acceleration up to the knee of the spectrum, up to 10 to the 15 electron volts. So these guys, the Cassiopeia, for sure produces accelerated hadrons at the lowest energies, but it doesn't go all the way to explain all the cosmic rays, all the galactic cosmic rays up to 10 to the 15 or 10 to the 16 or 17 electron volts. So supernova remnants apparently are falling short of maximum energy. And if you look at even higher energies with LASSO, this Chinese experiment, above 25 TeV, LASSO has made a real catalog of sources along the galactic plane for the first time at these extremely high energies. and they see a lot of supernova remnants. We knew all these from Cherenkov telescopes, but now we know that they go to even higher energies. Unfortunately, they look, and this is W51, where there's a supernova remnant interacting with some matter. Again, there's a cutoff at 100 giga-electron-volt, and it's very clearly cutting off. So you see a pi zero bump, but then you see a cutoff. So again, systematically, for all the supernova remnants we are looking at, we see a cutoff. So they don't make it. So if cosmic rays are not accelerated by supernova remnants, then what else is left that could accelerate cosmic rays? Well, you may have pulsars, and also from the last 10 years, we know that around pulsars, like Geminga, there are huge halos. And if the moon is like this, they are huge, right? They are huge halos of gamma rays, but unfortunately, they are coming again from leptons. So pulsars are probably accelerating the electrons and positrons, but not cosmic rays, not hadrons, okay, not protons. So we have to look for other sources. And there may be other sources. The sources at the highest energy galactic cosmic rays could be microquasars, for instance. I'm sure you know about SS433. Looks really like there's like a corkscrew. This is in radio. There's like a corkscrew running. There's a jet that is precessing, constantly precessing, and along the years is going around and is producing this funny structure in radio. This you could also see with an atmosphere, a Cherenkov telescope, HESS. And what you could see is not the microquasar itself, but you could really see the end of the jet. You can see gamma ray emission coming from the interaction point of the jet with some material in very far, like 100 parsecs away from the microquasar. The jet is interacting and is producing cosmic rays and producing gamma rays. Okay. Now with LASO at even higher energies, you still see something. Even beyond 100 tera-electron volt, you see gamma rays. And this must be coming from hadrons at even higher energies, more than 1 peta-electron volt. So these guys, apparently microquasars, are able to accelerate cosmic rays up to the highest energies. By the way, mind that maybe this is a technicality, but it's an important one. Mind that this is a typical angular resolution of a Cherenkov telescope. And this is the angular resolution of LASO, of a particle detector like LASO. So this is very small, much smaller than LASO. So that's why LASO only sees these big spots, and HESS can actually resolve all this structure inside this big spot. Okay, that's how Cherenkov telescopes and particle detectors actually complement. So there are some fellows that are actually trying to even model the cosmic rays that are produced by microquasars in the whole cosmic ray spectrum, and apparently fits. Okay, but this is still under discussion. So what about neutrinos? I mean, I told you it would be fantastic to get neutrinos from supernova remnants. Unfortunately, the sensitivity is not good enough. So you see, this is the galactic plane, and this is the galactic plane in gamma rays. This is optical. So in neutrinos, there's actually the galactic plane has been detected. Okay, it was published in 2023 by IceCube. So there's a neutrino emission coming from the galactic plane. So the galactic plane is bright in neutrinos, but it's impossible to see individual sources. These are just fluctuations inside a general flux of neutrinos. Okay. So unfortunately, we don't have a smoking gun yet. So we don't see a microquasar in neutrinos or a supernova remnant in neutrinos yet. Okay. So what happens at even higher energies is extragalactic cosmic rays up to 10 to the 18. So here there's no standard model, not even a standard model. So we don't know what the sources really are. Probably they are AGNs, maybe some GRBs, starburst, clusters of galaxies, and so on, all of the above, everything. And one interesting thing is that at the highest energies, 10 to the 18 electron volts, I told you that in general, cosmic rays are deflected by magnetic fields. But at the very, very highest energies, they are not deflected anymore because they have so much energy that they essentially go straight. So Pierre Auger has been taking data for like 20 years. And at the end, they got something like 4 sigma on the direction of Centaurus A. But that's all they got. And they have been observing for 20 years. So they still have to wait for a few more years to get a significant detection from some source of 10 to the 18 electron volt cosmic rays. Okay. There's an indication that also starburst galaxies may be producing in general cosmic rays of these energies. We are getting neutrinos from extragalactic sources. There's an isotropic flux of neutrinos. And this is very difficult to do. I will show you here, for instance, what IceCube published back in 2013, but this is the latest plot, just to illustrate how it works. So they detect neutrinos here as a function of energy. These are the data points. But then they have a huge background of atmospheric neutrinos coming from cosmic rays. And on top of this, at the highest energies, they got this excess of neutrinos that they attribute to extragalactic sources because they are isotropic. Okay, so it's a difficult game. You have to produce a spectrum with a very, very high background, up to 1 BD or so. KN3net has joined the game, and actually you probably heard the news that they detected 220 beta electron volt neutrinos during commissioning. Okay, it was very much in the news a few months ago. And if this is the spectrum that was detected by IceCube, I will show you where this neutrino is. So these are one I showed you before, 1 beta electron volt energies, right? This has been measured by IceCube. It has been now confirmed by KN3net as well. And they didn't detect any neutrinos at higher energies so far. IceCube operated for 10 years. So they could set upper limits. So if there are neutrinos, they might be down here. Well, this neutrino that was detected by KN3net would be here. It would be well above the upper limits. So there's something that doesn't quite fit here. I mean, it's significantly above the upper limits. We don't really know where it comes from. Okay, it may be somehow consistent, but it's rather puzzling result to get a neutrino at these energies, even one neutrino, okay, in a few months. So stay tuned to this because this will probably be a source of debate in the next year. Okay, what is good about the extragalactic neutrinos is we may be starting to see sources of neutrinos coming from outside our galaxy. The first one was this blazar, TXS0506, we call it Texas. Okay, this. And this was detected, I mean, by itself, it was only a few neutrinos, so it was not significant. So only a few neutrinos out of many neutrinos in some position, random position in the sky is not really significant. So you needed gamma ray detectors like Fermi, MAGIC, or HESS, or HAWK to tell you that there was a flare going on with this specific AGN near the position of the neutrino. Okay, so actually it was only one neutrino. So because you combine the fact that there was a flare in gamma rays at the same energies and some neutrinos coming from this direction, you get a significant detection, right? So unfortunately, after that, IceCube has been detecting more neutrinos from this source, but there's been no special activity in gamma rays. So there seems to be here some mismatch. Maybe this AGN sometimes is dark in photons and sometimes it's not. So this debate is also open here about this source. IceCube has claimed another source just by itself, no connection with gamma rays. After integrating for many years, they get an excess in some position that is already significant enough from NGC 1068. Okay, it's a cipher galaxy. Okay, this was published in 2022. So, and they are detected at 1 to 10 tera electron volt. It was detected by Fermi at low energies, but not by MAGIC. MAGIC made a very long exposure on this AGA. It was not detected by MAGIC. So you can make models. You can make a model where you produce neutrinos, but there's a very strong absorption of the gammas, okay, where you don't expect to see something in MAGIC. Okay, so strong absorption. You lose all the gammas at the highest energies, but you still see the neutrinos. Right. Is another dark source? Maybe. Okay, so what is next? What can we expect? So this is my wish list for the next years. So one is CTAO and LASO will go deeper in sensitivity. Okay, so maybe we detect a supernova remnant, even if only one supernova remnant in our galaxy that can go up to the knee. Even that supernova remnant may be enough to produce all the cosmic rays at the highest energies. So CTAO will actually resolve many of the galactic objects with a very good angular resolution, as I told you. So LASO has detected many sources at high energies. So we hope with CTAO we can look into the sources and see what are the specific emission points, okay? And learn how the cosmic rays are really accelerated. Hopefully we will see some pevatron, so some cosmic ray source at PeV energies in neutrinos, okay? So far, IceCube has not seen anything, but KN3-net, remember, it looks down. So it looks to the south. So it looks into the inner galaxy, where you have many more galactic sources, okay? So in that sense, KN3-net has an edge over IceCube. It's better than IceCube on that. So maybe it will detect some pevatron, maybe a microquasar, who knows? Okay. We need many more neutrino AGNs to understand if there's really a correlation with gamma ray sources, with gamma ray AGNs, or not. I mean, we have to study this systematically. We need many more AGNs, and that's something we will get with CTAO and with IceCube and KN3-net operating full time. Okay, so hopefully we will detect many, and we can make a population study, really. So maybe IceCube or KN3-net will detect a gamma ray burst, the neutrinos. I don't have big hopes. I mean, with MAGIC and actually LASO, there has been a detection of gamma rays beyond even 10 tera electron volts. But we believe that these are coming from electrons accelerated in the GRB. So probably GRBs are a leptonic source and not a hadronic source. But who knows? Okay, maybe we get a surprise here. And here is really essential that we are sharing alerts. So we get alerts for KN3-net from IceCube mainly, and vice versa. When we have a flare, we normally inform, they normally use that information in IceCube or in KN3-net in their analysis. Okay, so it's important to actually remain connected. And well, at the MEV range, a galactic supernova would be great. And it's long due, right? We are all waiting for this galactic supernova. Just to give you an idea, in Dune, this MEV detector in the US, you expect something like 3,000 neutrinos from a galactic supernova. Okay, with this you can do a lot, right? You can examine the time structure of the neutrino production in the supernova in millisecond scales, probably. Hyper-K, which is the Japanese experiment, is the same. You get thousands of neutrinos. Okay. Unfortunately, you go already to Andromeda, to N31, you get 3 neutrinos. Okay. So It's only for a galactic supernova. You need a galactic supernova. And here you will get, well, it will be fantastic, of course, in the whole electromagnetic spectrum, but we also have hopes of getting a prompt, so emission in the first hours in very high energy gamma rays. Okay. So that would be a big show. And I haven't touched on gravitational waves, as I'm sure you recognize, where there's also a strong connection through kilonovas, merger, short GRBs. We also we are looking for in gamma rays or dark matter. Sorry, Jorge, I did cover your favorite topic, but no dark matter today. That's a topic for the next seminar. Okay, so I want to end here. So.
Okay, thank you very much, Juan. Any questions? Yeah. If there's anyone in Zoom that has any question, please raise your hand or text it in the chat. Thank you.
Thank you, Juan, for the very nice talk. Regarding this high energy neutrino event detected by KM3net, what is the statistically the tension with the upper bounds from IceCube and I think it was Pierre Roger? Significant is 2, 3 sigma, 5 sigma?
This is IceCube.
Right.
Okay. So you may argue something like 2 sigma or so.
I see. Yeah. So, okay. So
Yeah.
there's a possible fluctuation, statistical fluctuation from Pierre Roger and IceCube. Is there any leading hypothesis how this can happen? But it's physical?
I mean, they are speculating maybe coming from what I call cosmogenic neutrinos. And these are cosmic rays at beyond 10 to the 18 electron volts that they interact they interact with light, okay, and they can generate neutrinos, okay. But if you make the numbers with the spectrum of extremely high energy cosmic rays that we have now, and you don't have enough neutrinos. You would end up down here. Okay, so you also have people saying, well, maybe there are a lot of cosmic rays even beyond this GCK cutoff. Maybe there's another population of cosmic rays or something like that. Okay. And then I think there are people talking about resonances and all that, but the glass of resonance is down here, so I think there's no obvious reason why. Yeah, so it's totally different energy, so nothing.
So, thank you very much for this very nice overview. I have a doubt regarding the sources with neutrino detections and intermittent gamma ray. Just a curiosity, which are the chances of emission coming from two different sources? I mean, something in the foreground, in the background, that is making the whole thing a mess.
If you consider the statistical chance, I mean, neutrinos, we speculate with two sources in the whole sky, right? And gamma rays, there are not so many. And so the density is very small. So I think the chances are very, very small. Yeah.
And another question, curiosity, which is the relevant time scale that you need for GRPs to be on source? I mean, because you're interested in prompt emission?
Mm-hmm. So we, at least in gamma rays, we always search for the prompt emission, right? So for long GRBs, you know that the prompt emission can last for some tenths of seconds, okay? So for instance, in MAGIC or in the LSTs, the telescopes are designed to go to any position in the sky in less than 30 seconds. So if we catch the prompt emission, it will be for a relatively long GRB or for a bright one or so on, okay? So we are still targeting the prompt emission. But the news was really that the GRB we detected in MAGIC, we saw the uptake loop, okay? So even after 1 minute or so, there's still a very bright afterglow. Okay. So in any case, we are targeting the prompt emission, which should be even brighter, right? And where we can learn even more. Yeah. I have to say for LASSO operates in a totally different way. In Cherenkov telescopes, you have to point to a specific region of the sky because your field of view is small, it's a few degrees. LASSO is open to a big part of the sky, like 60 degrees or something like that, it must be. So they were already there when there was this boat, this fantastic GRB. And so because they were on target, they could see the prompt emission. And that's why they got thousands, tens of thousands of neutrinos. Yeah. But they were lucky. They got lucky because the GRB was passing by. Okay.
Okay, any other question?
So can you go to your last slide where you were your wish list? So you mentioned here a lot of things you'd like to see CTA doing. You're not distinguishing between the north and the south. Is there any of those that you think the north is better or the south is better, or both, or is it identical?
Well, for some of them, for instance, galactic sources, you have more galactic sources in the south. Okay. For others, not. I mean, for AGNs and GRBs, it's the same all over the sky. And actually, in the north, we'll have the LSTs that go to lower energies, so you have a better chance to detect the source. If you get some absorption, remember this AGN, for instance, that you could detect in neutrinos and in Fermi, but not with magic. So with LSTs, maybe we have a better chance because we go to lower energies. Okay. But in terms of southern hemisphere and northern hemisphere, for galactic sources, the south would be better. And galactic supernova could be anywhere, right? In a way, could be also nearby.
Okay, any other question? If not, let's thank Juan again for the thoughts. And thank you all for coming, and see you in the next seminar. Thank you.
Deve essere extra galattico, cioè,